Before we get started on the Chapter 7 stuff, I want to talk about a couple of things real quick on the board. So at this point, since we're getting into a lot of reactions, you need to be building what I call roadmaps. And there's many ways to do it, but I think the easiest thing to do is to have a page for each reaction type. And so far, what kind of reactions have we talked about? We've talked about substitution reactions, right? And we've talked about substitution reactions primarily with alkyl halides. So one of the things you can do on your sheet of paper is start in the middle and draw an alkyl halide of some type. I'm just going to put RCH2X. And what I would do is put beneath whatever I'm doing there some notes, right? So like X can be, what can X be for a substitution reaction? Which halogen? It can be chlorine, bromine, or iodine. We know that fluoride's not a good leaving group, right? And so that's what I would start with. And then I would go from this and draw out the different types of transformations that I can do in each direction. And you're going to build kind of like a spider web of reactions that can happen. So, for example, we know we can take alkyl halides to what? Alcohols, right? Good. Okay, what do I need here? Pardon? Hydroxide. So we need some type of hydroxide nucleophile. Okay. And what kind of notes might I put with this? I can put SN2 if what? Well, what makes it an SN2 reaction?
That would be if it's a primary.
Okay.
If it's a primary carbon.
If a primary RX, right, for alkyl halide. Right. Okay, I might put polar aprotic solvent. Okay. We can get SN1 if a tertiary RX, right? And I might put water, or I can do this in water, right? If water would just be my nucleophile, then it would be a salicylic reaction. What else can I do to alkyl halides? Let's go off in another direction. I can make thiols. What kind of nucleophile do I need? It is a supernucleophile, but tell me what it is. Pardon? H2S would work, but here we need HS minus, right? So like we'd use sodium. I probably should go ahead and balance everything out. There we go. And what do I need here for a solvent? Yeah, and so this is going to be SN2, right? So we might do something like that, maybe make a few other notes. What else can I do to alkyl halides? What else can I make? Can make an ether. And what would I have to react that with? Some type of alkoxide, right? And I called it R prime. And I'm just going to use sodium. Okay? And that would be, this particular reaction has a name associated with it. Whose name is it? I think I heard it. Started with a W. This is the Williamson ether synthesis. Might put those types of notes there, right? This is SN1 or SN2? This is going to be an SN2. Right, I'm just going to put some notes there. What else can I do? We've gone from alcohols, thiols, ethers. What was another nucleophile that we did? Azide, N3, right? So we can make alkyl azides. Sodium azide, polar aprotic, right? Bless you. If Rx is primary again, we'll go through an SN2 reaction. I'm not going to go through all these, but you can start to build up a spider web or a roadmap, however you want to call it, of different reactions. And I know this is going to sound kind of corny to you, but these are things that you can study during commercials while you're watching television, right? You've got them all together. Commercials come on. Who wants to watch commercials anyway, right? It's not the Super Bowl. So you pull out a sheet and you go over it real quick. And what this will help you do is figure out how you can convert a particular functional group into a variety of other functional groups. And then as we learn more reactions, we're going to learn reactions of alcohols. You'll have a page that's just alcohols. And so you'll know that you could go from an alkyl halide to an alcohol, and then from that alcohol, that other page, you can do all kinds of stuff with. Okay? So it's a really convenient way in my mind to keep track of all these things, and it's also an easy way for you to study, because you can literally pull one of these out in 4 or 5 minutes during a commercial break, and I'm not kidding. You can refresh your memory. Because remember, one of the things that Liberico said is you need to think about the material all the time. Well, now, I know you're not going to do it all the time, right? But in these little quick breaks, you can pull something like this out, and it's a heck of a lot more convenient than opening your book and trying to figure out where all the reactions are. Now, you need to read, but it's not as convenient to do these quick study things as it would be to do this. And as time goes on, if you organize your paper right, you'll start to see that there'll be additional reactions that you'll add as we go through different chapters. And this will build up, and this is a great way for you to, at least mentally, keep track of what you need to know, okay? So right now, at least what we've talked about, right, we know how to make alcohols, thiols, ethers, and azides from alkyl halides, and there are others that we talked about as well. You know how to make esters, right, for example. You can make carbon-carbon bonds. We'll talk more about those later, but all that can be placed on this one page. Are there any questions about roadmaps? Yes. Which one? Here? Usually this one is done in alcohol, so polar protic, simply because the alkoxide is usually dissolved in the alcohol that it was made from. But it's a great way to organize your thoughts, study quickly, okay? While you're waiting in the line at the fresh, whatever the case may be, you can pull one of these things out, study up a little bit, and you'll be surprised how 5 minutes here, 5 minutes there can make a really big difference in how well you recall this type of stuff. All right, so today we're going to get into chapter 7, and at this point we've been talking about addition reactions, or substitution reactions I should say, where we are substituting something for a halide, right? And that's where the Lewis base is functioning as what? A nucleophile, right? But sometimes Lewis bases function just as bases, and they go after protons. And when they do that with alkyl halides, you actually undergo what's known as an elimination reaction. And you eliminate HX, a hydrogen and a halogen. And you get an alkene out of it. So it's a great way to make alkenes, okay? And so we're going to talk about these elimination reactions, and we're going to hopefully get to where we talk a little bit about the mechanisms of those eliminations today, okay? And then my goal is to hand back your exams as you leave for class. But on Wednesday, I need to let everybody know this. On Wednesday, we're going to have a demonstration in here. You need to bring a device. It can be your phone, a tablet, whatever you have that can do video, because you're going to have to video the demonstration for the video project, okay? And I'll give you more details about that later. But during Wednesday morning, we're going to do, first thing, a demonstration on leaving groups, okay? So the general feature of an elimination reaction is simply removing a hydrogen and a halogen from adjacent atoms to give a new pi bond, an alkene, okay? We call this beta elimination. Can anybody tell me why this is known as beta elimination? Beta carbon. Okay, what on the beta carbon? The pardon? Okay, so if the halogen was on the beta carbon, how would we know which carbon was alpha? But I could have other carbons on there that it's flipped. That's exactly right. The one bearing the halogen is the alpha carbon, and all the carbons attached to it are the beta. So we're removing the hydrogen from the beta carbon, okay? And so we call this beta elimination, okay? And we are removing, what are we essentially removing from that molecule in general terms? A proton and what? And a halogen, which is really what? HX, which is typically considered what? An acid. That's right. We are eliminating a strong acid, right? HCl, HBr, and HI are all strong acids. So we are eliminating a strong acid from an organic molecule to generate an alkene. If I want to remove an acid, I need a what? A base. And that's how you remember this, okay? Anytime you want to neutralize an acid, if you will, you use the base, right? And so the same thing is going on here, except instead of neutralizing, we're just eliminating the elements of a strong acid from an alkyl halide to give us a new pi bond, an alkene. And it turns out that alkenes are very, very useful functional groups in and of themselves. So having methods that we can use to make alkenes is very, very important, okay? So here's a couple of examples. Here we have, how would we name that molecule? 1-bromo butane. Very good, right? And we have to have the 1 there because we could also have 2-bromo butane, so on and so forth, right? And we are reacting it with what? How would you name that? It's potassium tert butoxide. Yeah, close, right? So this is potassium tert butoxide. Is this a base or a nucleophile? It says base, right? But why is it not a nucleophile? Steric, that's right. We've got all that stuff on the T-butyl group, right? It's a very, very poor nucleophile, but it's a pretty darn good base, right? And so what happens is, right, this reacts and we eliminate HBr, and we end up with an alkene. Notice that the carbon-carbon double bond is between the carbons of the elements that we eliminated. Okay, so we eliminated hydrogen from this beta carbon, we eliminated the bromine from the alpha carbon, and that's where the pi bond is. And so now we have, how would we name this? 1-butene, that's right. So we end up with 1-butene. Here we have, how would we name this? Would I need a 1? Yep, so it's chlorocyclohexane, right? So we have chlorocyclohexane. We are using sodium ethoxide. We are eliminating HCl, and we're getting cyclohexene as our product. This one might create a little bit of a problem for us, though, right? Why? It can also be a nucleophile, right? So here we show it acting as a base giving an alkene, but this could also be nucleophilic. And so we know that secondary alkyl halides can function as good substrates in SN2, right? So it's possible that we could get SN2 type chemistry here as well. However, I can tell you that there are ways in which to ensure that we're going to get the elimination. One is we have the chlorine instead of an iodide or a bromide. So is chloride a better leaving group? No, it's not, right? So poor leaving groups typically favor elimination. And also what's not indicated here is you would probably heat this reaction up a little bit, and heat typically favors elimination over substitution. That's another tidbit that you need to kind of commit to memory. So we can actually get elimination reactions. This one we don't have to worry about substitution at all because we know this isn't going to be a nucleophile. Here we would have to pay attention to our reaction conditions. Okay? As I mentioned earlier, this is known as beta elimination. And the particular mechanism that we're going to be talking about right now looks very similar to what kind of mechanism that we talked about before. We've only talked about 2. We've talked about SN1 and SN2, right? That mechanism, does it look more like an SN1 reaction or an SN2 reaction? And why do you say that? Okay, so we're seeing something come in from the back. What else tells you that this looks like an SN2 reaction? All right, so we have both the base and the alkyl halide involved in that rate determining step, right? So that's very similar, and we have just a single step. The difference is what? Where's the difference between this and an SN2 reaction? In an SN2 reaction, what would the base be attacking? A carbon, right. And it's not here, right? It is attacking this hydrogen, and we're eliminating HX. What can you tell me about the relationship of the hydrogen that's being eliminated and the halogen? They are kind of trans to one another, right? Does that make sense? Pardon? Kind of like in an SN2, right? All right. So that's exactly right. So we know that these electrons right here in this carbon-hydrogen bond are going to be the electrons in the pi bond. Okay? So those electrons are coming in from the back, if you will, kicking out the halogen. Okay? And so the base has to approach the hydrogen that's kind of trans to the leaving group. This is where your model kits are going to come in handy. Because especially when you're talking about cyclic substrates, not all hydrogens can be eliminated. They have to be trans to the leaving group. And so you'll have to look at a model to see which hydrogen actually gets eliminated. Okay? Okay, so notice how many arrows we have involved. What kind of arrow are we using? Double. We're pushing pairs of electrons, right? So the pair of electrons from the base is coming in to react with the proton. Okay, how many bonds can hydrogen have? One. So we have to be breaking the carbon-hydrogen bond, right? And those electrons, notice how they have them kind of going here to show the pi bond, and then the leaving group is leaving, okay? So this is known as not an SN2 reaction. Can anybody tell me how this one is described? E2. E for elimination, 2 for bimolecular. That's exactly right. So what would the rate of this reaction be if Aubrey came into the lab and doubled the concentration of base? It would double. What happens if Grace doubled the concentration of alkyl halide? And what if somebody came in and doubled both? Quadruple. So you should see that there's a relationship between SN2 and E2 and a lot of the physical things that we're going to be talking about. Even the mechanisms are kind of similar. The difference is the product that we get. In an SN2 reaction, we get a substitution. In an E2 elimination, we get an elimination, get an alkene product. Okay?
We were doing this in Saffron, correct? This last chapter.
It was covered a little bit, yep.
I couldn't understand it, but I did.
There are some common bases that you need to have committed to memory for what is known as dehydrohalogenation. Okay? Sodium hydroxide, potassium hydroxide, these are no-brainers for you, right? You all have talked about those until we're blue in the face from Gen Chem on, right? Every titration you probably did involved one of these, right? Sodium methoxide and sodium ethoxide are also common bases used in dehydrohalogenation. And then potassium tertbutoxide. Tell me what the advantages and disadvantages of these 5 molecules are. Let's start with sodium, let's start with a group. Let's start with sodium and potassium hydroxide. What are some advantages of using sodium and potassium hydroxide in this reaction? They're relatively strong bases. Good. What else? Go to any lab, you'll find a bottle of sodium hydroxide or potassium hydroxide. It's relatively common, right? What are some disadvantages? They're also nucleophiles, so you have to worry about substitution versus elimination. And what else? Are sodium hydroxide and potassium hydroxide soluble in organic solvents? Not easily, right? Not easily. You won't find them in things like THF or ether or anything like that. They don't dissolve. They dissolve in things like water. They will dissolve in alcohol, okay? But they're fairly insoluble. Okay, so those are some disadvantages. How about the alkoxides, methoxide and ethoxide? What are some advantages? Okay, they're fairly common. They're easy to make. Anybody know how you make sodium methoxide and sodium ethoxide? Do some magic? Okay, yeah, so you start off with, if we want to make sodium methoxide, we start off with methanol. And in fact, if you came to my lab, I don't think you'll find a bottle of sodium methoxide around because we make it when we need it. But what you will find a lot of in my lab is metallic sodium sitting in a vat of oil. Okay? And so if we ever need sodium methoxide, we take some freshly distilled methanol. We put it in a flask, we cool it down, and then we take the number of moles of sodium that we would need, and we weigh it out, and we wash off the oil, and we cut it up into little tiny nuggets, whatever, little small pieces, and we sit there with a pair of tweezers, and we slowly toss that into the methanol. Anybody know what happens when you toss sodium into methanol? Well, it could, but if you're careful, it doesn't blow up.
What do you wash it with? The oil with?
Hexane.
Okay.
Yeah, we just use some non-polar organic solvent, non-polar, non-protic solvent. You actually start getting hydrogen bubbles, and it looks like the metal is dancing around the surface of it, and it's kind of, but you can make sodium methoxide very, very easily that way. You can also make sodium ethoxide very, very easily that way. And that's why I mentioned on the roadmap problem where we made the ether through the Williamson ether synthesis, I told you that the alkoxides were typically in their alcohol, because we usually use an excess of alcohol, add the sodium slowly, make the sodium methoxide or ethoxide, and then simply just add the alkyl halide to it to do the Williamson ether synthesis. So that's why they're typically in those solvents. What are the advantages of, another advantage of these? They're easy to make, they're cheap, they're also soluble in organic solvents, right? So these are soluble, whereas sodium and potassium hydroxide are not, right? These are made in alcohol, but you can also react these or dissolve these somewhat in other solvents as well. And potassium terbutoxide, what are its advantages? Non-nucleophilic, right? So we know we're going to get elimination chemistry going. What else is an advantage? Is it a stronger base or a weaker base than sodium or potassium hydroxide? What's the pKa of sodium or potassium hydroxide approximately? It's about 16. Close? It's water, right? 15.7. So what's the pKa of potassium terbutoxide? No. Not close. Where's it at? A little bit above or a little bit below sodium or potassium hydroxide? It's a little bit above. And it turns out that it has a pKa of around 18 to 19, somewhere in that ballpark. Okay? So it's an alkoxide that's non-nucleophilic that's actually stronger than hydroxide. Okay? And so it works really nicely in these elimination reactions quite well. Okay? So let's look at some examples. And in these examples, we're going to just use simple bases. Okay? We don't have to worry about substitution here. Why? So why can we get away with sodium hydroxide? Yusuf said that this was a good nucleophile, so why do we not have to worry about it being a nucleophile here? Because it's tertiary, right? Very good. And so even though we've got a strong nucleophilic base, we've got a tertiary alkyl halide, it's not going to do SN2 chemistry, right? So notice in this case, all of our beta carbons are exactly the same. So does it matter which hydrogen it takes? It's got to be trans, but you got 9 of them. And each one of these carbons will have one that is trans to the bromine. Okay? So it doesn't matter which carbon we take it from here. You'll end up with the same product. Okay, so we go from 2-bromo, 2-methylpropane, treat it with sodium hydroxide, and we get what's known as isobutylene. It's a gas. And so we know that this reaction goes very, very well because you have a liquid, you drip it in, and you start to see this gas come off, which is this. Okay? And we only get one alkene product form. However, if you look at this molecule, are the 2 beta carbons the same? No. And how are they different? This beta 1 is what kind of carbon? It's primary. It is a methyl group, right? I think I heard somebody say that. But it's primary, and it's primary because it's bound to only one other carbon, right? This beta 2 carbon, however, is what? It is secondary because it is bound to 2 other carbons, right? So if we think about removing one of the hydrogens, right, we've got one here that's trans to the bromine. We can get an alkene here between beta 1 and the alpha carbon. If we imagine eliminating this hydrogen, which is also trans to the halogen, we would end up getting this alkene. And how are these related? They are constitutional isomers. Do they have the same physical properties? No, they do not, right? And so 2 possible alkenes can be formed. Take a guess as to which one is formed in greatest abundance. The first one? Okay. Why do you say that?
Because it's easier to get the hydrogen off that front. Wait, no, I'll change my mind.
Ah, I changed my mind.
I'm all in now.
Okay, you're all in. All right.
I'm sure it is, but I'm still
Okay.
thinking second one.
No. Make your argument.
Okay, so it's easier to get the hydrogen off the primary carbon.
Why?
So here's mine.
Because it's less stable.
Because you know, the more carbon groups you have, the more orbits you have.
It's less sterically crowded. Is that what you're... Okay. Okay. We'll go with that. That's not a bad argument. What's your argument?
Okay, so does an SN2 like primary carbon?
Are we doing SN2?
Exactly. We want the opposite. So,
We want the opposite.
so we want
Okay.
carbon with the most stuff on it.
All right. It turns out both arguments have a certain amount of validity. Okay? However, what is controlling this is the transition state, right? And the transition state is more product-like. It looks more like the products than it does the starting material. Which one of these products is the most stable? Why is this the more stable product? It is symmetrical. More stuff. Okay, you're on the right track. It's the more substituted alkene. And we know that the more substituted the alkene, the more stable the alkene is. And we know that should know that through the reading before you came to class. But also, we know that from experiment, which we'll talk a little bit about here in just a moment. Okay? Huh? And under the conditions that we're talking about now, you're right. But there are conditions where Aubry would be right. Okay? It's a question of a thermodynamic. What Yusuf was talking about was a thermodynamic property, stability, and really what you were talking about was a kinetic property. Yeah, that's right. So the pi bond, right, looks something like this. And we've got a sigma bond in between, and then the pi bond is above and below the plane. What do we know about the strength of pi bonds? Weaker than what? Sigma bonds. Now, you all have probably learned in the past that a double bond is stronger than a single bond, right? That's true when you're taking the sigma and the pi together, right? So keep that in mind. But the pi bond is the weaker of the two bonds, right? And why is it weaker than a sigma? Okay, so there is restricted rotation, that's true, but why is the pi bond itself weaker? Pardon? Less overlap. That's right. So the p orbitals, if we look at them, right, how are they overlapping one another? Just on the sides, right? But a sigma bond is overlapping head to head or tail to tail, however you want to think about it, right? And so you have a lot of orbital overlap in a sigma bond. You don't have a lot of orbital overlap in a pi bond, and that's what gives us all of our bond strength. Okay? Now, there are several different types of alkenes that you need to know. There are monosubstituted alkenes, where you have the carbon-carbon double bond and only one additional carbon atom attached to that alkene. Okay? These are known as monosubstituted. You will also hear me call them terminal alkenes. Why would I call that a terminal alkene? Because it's at the end. That's right. And it's also known as an alpha olefin. Okay? For those of you in polymer science, they probably talk about alpha olefins a lot, or olefins. Olefin is just another word for alkene. Okay? Alpha olefin meaning that it is terminal, okay? Alpha. Huh? Oh, very good. We have disubstituted alkenes, where we have two R groups that are attached to the carbon-carbon double bond. Now, we can have multiple types of disubstituted. Notice here, the two R groups are attached to the same carbon. But we can also have one of the R groups attached to this carbon and the other one attached to this carbon. So you can have kind of a terminal alkene, if you will, here that's disubstituted. This is not an alpha olefin per se. We can have trisubstituted alkenes, where we have 3 carbon groups attached to the alkene. And we can have tetrasubstituted, which is 4 carbon groups attached to the alkene. So if we look at some common ones, right, here we have a monosubstituted. What's the name of this one? 1-butene. Here we have a disubstituted. Okay, notice that we're using these little colored spheres to indicate the substitution. Right, how would we name this one? Cyclohexane, and here, cyclohexene, excuse me. And here we have a trisubstituted alkene. Okay? Now, we all know that butane has nothing but sigma bonds, and we can have free rotation around sigma bonds, right? And we were talking about whose projection? Newman projections, right? So we can look at a variety of Newman projections. If we look down this bond, this is the most stable arrangement. And why? That's right. These two methyl groups are 180 degrees apart. Everything is staggered. This would be what? Yeah, but what is it on the energy diagram? That's the highest, right? So you're getting these big groups in the way of each other, right? But these can actually interconvert fairly easily by free rotation around the carbon-carbon single bond. However, when we put in a carbon-carbon double bond, we've actually stapled this molecule into a particular conformation, if you want to use a layman's term, okay? We can have 2 possibilities for butene, 2-butene, right? We can have the 2 methyl groups on the same side, which is the cis conformation, or the cis isomer, and we can have the 2 methyl groups on opposite sides, so these are trans. These will not interconvert readily. Why is that? That's right. I can rotate freely around a single bond, but when I put another bond in, what happens if I try to rotate? I have to break a bond. And what do we have to do to break a bond? We have to use energy. I can take cis 2-butene and convert it into trans 2-butene if I shine a really bright light on it. And that light is providing the energy needed for that transformation to occur. But it has to break the bond, then rotate, and then the bond form again. Okay? Which one of these is more stable, the cis isomer or the trans isomer? And why? That's right. We've got the groups as far apart as we can, right? So same types of arguments are going to be invoked here. Okay? These are diastereomers. So what would we expect? They are different molecules, and therefore they have different physical properties. That's exactly right. However, everything's connected the same way. They are not constitutional isomers, right? They are stereoisomers. Okay, this is 2-butene, and this is 2-butene. The only difference is this prefix, right? Which tells us how those groups are in 3-dimensional space. So these are stereoisomers with respect to one another, but they are not chiral. Okay, we do not have R and S type stereochemistry. This is cis versus trans. Okay. Now you have stereoisomers when the groups that are attached to the alkene are different. Okay, so that's pretty easy to see. So if you have an X and an X prime, a Y and a Y prime, you can have stereoisomers. If you have X and X, you will not have stereoisomers, right? Because you won't have cis versus trans. So these groups must be different from each other. Okay. So for example, here we've got a methyl group and we've got a hydrogen. Those are 2 different groups. Here we have a hydrogen and a methyl group, 2 different groups. And so we can have trans and we can have cis, right? And we talked about the trans being the more stable because these groups are actually farther apart. If you actually build a space-filling model, not your little models that you have, but a space filling that actually approximates the size of atoms better, which we can do on the computer, you'll actually see that these hydrogens in this cis actually start to touch each other. It's a serious steric crowding. And so, as you would expect, the trans isomer is much more stable than the cis isomer. You need to know the stability trend. And it turns out that the more alkyl groups you attach to an alkene, the more stable that alkene is. So here we have ethylene. Okay? So it's a very simple molecule, not substituted at all. Everything's hydrogen. It is the least stable of the alkenes. It is also one of the most industrially useful of the alkenes. Why? What's ethylene used to make? Yeah, well, that's true. Although we don't use it in antifreeze anymore. We use propylene glycol. Can anybody tell me why? Anybody know why? It's better for somebody. Animals, that's right. Ethylene glycol is highly toxic. Propylene glycol is not. And people used to change their antifreeze and just leave it out in the yard in a bucket, and it's extraordinarily sweet. And animals would come up and take a lick and then keep licking and die. That's right. And kids would die from it too. So ethylene, it's also used to make polyethylene, for those of you in the polymer science areas, right? Heavily used plastic. So it's less stable than a monosubstituted, which is less stable than a disubstituted. Notice that the disubstituted, where the two substituents are on the same carbon, is about the same stability as having them on different carbons. But both of these are less stable than a trisubstituted, which is less stable than a tetrasubstituted. And we know this because of combustion. Okay? So you all did a calorimetry experiment in Gen Chem, right? Right? Okay, and you guys use coffee cups. You can't use coffee cup calorimetry here. Okay? But if you take these molecules and you burn them in the presence of oxygen, you get carbon dioxide and water and heat. And we know we're going to get heat. Why? Because when you burn a hydrocarbon, it gets hot, right? And so if you burn this hydrocarbon, you get 2717 kilojoules per mole of heat. If you burn this hydrocarbon, you get 2710. If you burn this, you get 2707. If you burn this, you get 2700. Okay? The more stable means it's lower in energy, right? And they're all going to 4 carbon dioxides and 4 waters. So the amount of heat that we get out of burning these things tells us how stable these molecules are. Okay? And so you can actually get a lot of information by just burning something. Okay? And so we know now that a monosubstituted is less stable than a disubstituted, and the trans is more stable than the cis, so on and so forth. Any questions about that? All right. So now we need to talk about the mechanisms of elimination. We've already established that there's going to be an E2 mechanism, right? There's also a corresponding E1 mechanism. Absolutely. And so what would E1 stand for? Unimolecular. That's right. What's it going to go through? What's going to be an intermediate? What was the intermediate in the SN1 reaction? And we're going to have a carbocation here as well. Okay? Again, a lot of similarities to both reactions. Just the big difference is what you get out as your product. Okay? So we know that E2 and E1 are going to differ by the timing of bond breaking and bond forming. Okay? And very analogous to SN2 and SN1 reactions. We've already talked about a lot of the similarities. The most common, or the most useful actually, is the E2 mechanism because it gives us cleanly alkene products. It does exhibit second order kinetics, so you would expect that the rate is going to be proportional to some rate constant times the concentration of the alkyl halide and the concentration of the base. Okay, in this case they're showing hydroxide, that's okay. The reaction is concerted, right? What do I mean by that? I know what it says up there, but what does it mean to say that it's concerted? All done at once. What do you mean by that? It does happen very quickly. It happens all at once. But what do we mean by that? What does it all happens at once mean? Okay, all the bonds that are breaking and forming are happening at the same time. That's exactly right. So as that carbon-hydrogen bond is breaking, we've got a carbon or a hydrogen base bond that's forming. We've got a pi bond that's forming, and we've got a leaving group that's leaving. All at the same time, okay? And so, again, if we look at our example, in this case, hydroxide can only function as a base. Why? Yeah, that's right. It's tertiary, so it can only grab a hydrogen. And in doing so, we're forming a bond between hydrogen and OH to make water. We are breaking this carbon-hydrogen bond to make a pi bond, and the carbon-halogen bond is leaving to make bromide, right? And so all those steps are happening at once, and this is an E2 mechanism. Yes, sir?
Is that why SN1 reactions favored weak base, because a stronger base would do the proton and swap over, like would do the elimination instead of substitution?
Yes. Essentially, yes. So notice that the reaction energy profile is very similar for an E2 and an SN2 reaction. We've got starting material, we've got products, and we've got a single hump, right? A single energy of activation. There is no carbocation intermediate. And notice what the transition state looks like. The transition state starts to have an alkene in it, right? And that's why the more stable alkene typically forms, because that's going to be related to the more stable transition state, right? And whose postulate gave us all that? Hammond's postulate, right? Very good. Okay? There are two other bases that you need to know, at least by their three-letter acronyms. I am not going to care if you can draw these on an exam, okay? But other bases that are very useful in E2 reactions are DBN and DBU, okay? Diazobicyclononane, diazobicycloundecane. DBN, DBU, good enough for me, okay? Both of these are really good bases for E2 eliminations, okay? The nitrogen is basic, and it turns out that it's this nitrogen that functions as the base, not this nitrogen. And I want you to think about this when you go home tonight and come back with an explanation on Wednesday. Why should this nitrogen be the base and not this nitrogen? So the nitrogen that is sp2 hybridized is the base in both of these. Okay? Think about that and come back with a plausible answer. Okay? Look up on the internet if you want. I don't care. All right? What's the advantages of these bases over, say, hydroxide or alkoxide? They're very organic soluble, and you can get them into polar aprotic solvents very, very easily. Okay? So you can run them nicely in organic solvents that are typically used. Okay? They're a little more expensive than the other ones, but they do their job quite nicely. Okay? Let me give you an example of an E2 elimination that has been useful. E.J. Corey, I believe, did this reaction many, many years ago. He's a Nobel Prize winner in organic chemistry back in the 90s. He used DBN to react with this alkyl halide to put this double bond right where he wanted it. And then he took this and converted it into what's known as a prostaglandin. Anybody know anything about prostaglandins? These are the molecules which are responsible for pain. When you all get to medical school, you're going to learn about prostaglandins until you're sick of them. They are responsible for pain, arthritis, inflammation, headaches, all kinds of stuff. And there's a whole series of prostaglandins that get synthesized biologically. And we needed to synthesize standard prostaglandins so that we could analyze them properly. And E.J. Corey figured out how to do that quite conveniently. Okay? But he used, no kidding, sophomore level organic chemistry to at least do the first step to put the pi bond where it was. The other stuff, just take this and put it in dilute acid and you make this very, very easily. And we'll learn more about these types of steps later on. Okay? That was the trick. Okay? So we're going to stop there. I've got your exams. Now, I have paperclip to all of you your exam if you're eligible to do the redo. Okay? So the redo will be due on, what did I say, close of business Wednesday? Something like that? So if you don't want to redo it for whatever reason, it needs to be returned to me by Wednesday, okay? And follow the rules that I gave from the previous